أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي رب يسر ولا تعسر وتمم بالخير. Assalamu alaikum wa rahmatullahi wa barakatuhu. So today's our lecture of linear control system is 15. So in this lecture video, we will be discussing about the canonical forms. So in the previous two videos, we have seen the controllable canonical form and the observable canonical form, and we have seen that how with the small manipulation of the transfer function, we can obtain the different forms of the state space model. So today's video we will be looking at the another canonical form which is known as the diagonal canonical form. So diagonal canonical form is actually obtained for the system which has the distinct eigenvalues plus we use the partial fraction to separate these terms so that we can get the diagonal canonical form. So to understand it, let's just look at one small example. So I hope so that example will be enough to make it understand how we can obtain the diagonal canonical form, because as the name suggests, it contains something important in the diagonal form of the matrix. So what's that important thing is? Let's look at this example. So it is 2s plus 5 over s square plus 7s plus 10. So the first step is to find out the roots of this equation, which are known as the poles or the eigenvalues of the system. So first of all, we need to calculate these eigenvalues, and then we will see how we will use those eigenvalues or the poles of the system. So the characteristic equation of this system is s square plus 7s plus 10 is equal to 0. So it's a simple quadratic equation, so you can solve it in many ways. So but it's okay. Then the solution of this equation is -2 and -5. So it means that we have these two eigenvalues, lambda 1 is equal to -2 and lambda 2 is equal to -5. So these are our eigenvalues for this system or the poles of this system. So what we will get this transfer function then, ys over r of s is equal to 2s plus 5 over s square. Sorry, we'll write in the form of these roots then, s plus 2 s plus 5. Okay, so by partial fraction, I hope you know the partial fraction, so you can solve it. So we just need to calculate these a and b by using this relation. So here a will be simply a comes out to be 1 by 3 and b is simply 5 by 3. So we will get this relation as y of s over r of s is equal to 1 over 3 by s plus 2 plus 5 over 3 by s plus 5. Now these are two different small transfer functions of first order system. So we will draw its block diagram to make it more elaborate to understand this method actually. So it's simple. We have this r of s at the input and y of s at the output. So r of s actually goes to these both transfer functions, means we will write it as 1 over s plus 2 and 1 over s plus 5, and we will make small block gain block 1 by 3 here and here 5 by 3. So they will sum up here and will produce y of s. So we call this first output as x1 of s and x2 of s. Now from this block diagram, we can write this y of s is equal to 1 over 3 by s plus 2 into r of s plus 5 by 3 by s plus 5 into r of s. Okay. Now this can be also written as 1 over 3, 1 over 3, because Rs over s plus 2 is x1 of s, and Rs over s plus 5 is x2 of s, 5 by 3 times x2 of s. So it means that x1 of s is R of s over s plus 2, and x2 of s is R of s over s plus 5. Now taking one equation at a time, so what we will get from here is s plus 2 times x1 of s is equal to R of s. Now taking the inverse Laplace transform, taking inverse Laplace transform, so what we will get here, we will get it x1 dot plus 2 x1 is equal to R of t. Now similarly for the other equation, for this equation, okay, just we write another with another color, so it is s plus 5 or into x2 of s is equal to R of s. Now again taking Laplace transform of this, so what we will get, x2 dot plus 5x2 which is equal to R of t. Now we have transformed these two these transfer function into two first order differential equations. So we can write it in the form of now matrix form. Okay, so means before that we can do it one more step. X1 dot is equal to minus 2x1 plus R of t, and here it will be x2 dot is equal to minus 5x2 plus R of t. So now we can write this in matrix form. So it will be x1 dot x2 dot which will be equal to x1 x2 plus input vector times R of t. So x1 dot is equal to minus 2 x1 and 0 x2 and 1 times R of t, and x2 dot is 0 times x1 minus 5 times x2 and 1 times R of t. Okay, now similarly this is our state equation. Now similarly the output equation can be formed here for here y of s. So y of s is actually 1 over 3 times x1 of x and uh, plus 5 by 3 times x2 of s. So y of s can be written as output equation, output equation. So output equation is y of s is equal to 1 by 3 x1 of s plus 5 by 3 x2 of s. Now taking the inverse Laplace transform, taking inverse Laplace transform, so we will get y of t is equal to 1 over 3 x1 plus 5 by 3 x2. So output equation then will be y is equal to 1 by 3 5 by 3 x1 x2. Now here most important thing why we call it diagonal, we here can see that the diagonal of this system matrix are the roots of this transfer function or the eigenvalues of this system. So every other element will be 0, even if it is a third order system, fourth order system, fifth order system, whatever it is. Okay, now let's see another canonical form which is known as the Jordan canonical form. Jordan canonical form. So Jordan canonical form basically is obtained similar with the similar method as we have obtained the canonical diagonal canonical form. The only difference here is that in Jordan canonical form we will have some repeated eigenvalues. So whenever we have some repeated eigenvalues, we will have the Jordan block in our system matrix. So that's why it is called the Jordan canonical form. We will see how this Jordan block actually looks like. Sometimes we call it the diagonal canonical form is considered as the special form of the Jordan canonical form. So to understand this again, let's look at an example so that we can have the clear picture of this Jordan canonical form. So we will see a third order system so that we can understand the Jordan block in our system. So y of s over r of s is given as 2s square plus 2s plus 3 over s plus 1 square and s plus 3. So here we have the two eigenvalues which are repeated, and one is different from either. So we have two eigenvalues, and one is repeated eigenvalue. So how we will proceed it? Again, it is the same procedure that we have to solve it through partial fraction. So after partial fraction, what we will get here is 2 over s plus 1 whole square plus 1 over sorry, it's a minus 1 over s plus 1, and then it is plus 3 over s plus 3. So here we can actually look at this system, and what we will how we will proceed further. Uh, so let's make a block diagram of it first, and we will see how it looks like. So we have this r of s, and obviously this is y of s at the output, and we have this r of s going to the uh, 1 over s plus 1, s plus 1, and then again it is 1 over s plus 1, so it will be s plus 1 square times uh, times its gain, uh, which is actually 2 here, this one, and then we have summed up here at plus, and then we have another gain that's coming here, which is 1, that will be summed up here, and then we have this 1 over s plus 3 and multiplied by 3, so that will be summed up here. So this is our block diagram. Uh, so we just need to label the state variables here. So we call it here as x1 of s, here x2 of s, and here we call it as the x3 of s. So obviously, as we have a third order system, it must be the three state equations for it. So how we will proceed then? So x1 of s will be simply uh, x2 of s divided by s plus 1. Sorry, before that, before writing in the form of this, we will write it all these three equations first. So that will be r of s divided by s plus 1 square, and similarly we will have x2 of s. x2 of s will be equal to r of s, and x3 of s will be r of s over x plus sorry, s plus 3. So we have these now three equations, so we will just proceed as so from these two equations we can write it as x1 of s is equal to x2 of s, x2 of s over x plus 1. Okay, so I think so it's quite easy to understand this step. So we rs over s plus 1 is x of 2, so that's why we have written it here. So or we can write it as s plus 1 into uh, x1 of s, which is equal to r of s. So taking inverse Laplace transform, so what we will get is x1 dot plus x1 is equal to r of t, which implies that x1 dot is equal to minus x1 plus r of t. So we call this equation as A. So from the second equation, x2 of s, so x2 of s is equal to r of s over s plus 1. So that can be written as uh, s plus 1 into x2 of s is equal to r of s. Taking inverse Laplace transform, it will be x2 plus x2 is equal to r of t, or we can write it as x2 dot is equal to minus x2 plus r of t. Sorry, we have made this small mistake. This is not r of s, this is not r of t. So as we can see, it is x2 of s, so it will be x2 of s, it will be x2, and it will be x2. Okay, so there will be no r of t here. So second x2 dot will be minus x2 plus r of t, so we call it as the b. Now from the third, x3 of s, which is r of s over s plus 3. So or we can write it as s plus 3 into x3 of s, which is equal to r of s. So taking inverse Laplace transform, it will be x3 dot plus 3 times x3 is equal to r of t, or we can write it as x3 dot is equal to minus 3x3 plus r of t. So from these a, b, c equations, we can write down their state equation. So that will be x1 dot, x2 dot, x3 dot, that will be a 3 by 3 matrix, x1, x2, x3 plus input vector and then r of t. So from equation A, we can write it as minus 1 times x1, 1 times x2, and 0 times x3, and 0 times r of t. For from equation B, we can write it as here we can see x2 dot is only minus x2, so it will be 0, minus 1, and x3 is again 0, r of t is 1. Similarly, from this equation, C equation, so we can write it as 0x1, 0x2, minus 3x3, and 1 times r of t. So here we can see that this important phenomena, which we call it as the Jordan. So this is called the Jordan block. So every repeated eigenvalues, even if it is a fifth order system or sixth order system or 10th order system, if we have the repeated eigenvalues, we will obtain this Jordan block. This is called the Jordan block in the system. So similarly, y of s will be simply output equation will be simply y of s is equal to 2x1 of s minus x2 of s plus 3 x3 of s. Okay, now just taking the inverse Laplace transform, so y of t will be equal to 2x1 minus x2 plus 3x3. So it will be y of t will be equal to 2 minus 1 3, and it will be x1 x2 x3. So here we have seen these Jordan block in this Jordan canonical form. So remember that the Jordan canonical form is obtained when we have the repeated eigenvalues. It could be the one repeated eigenvalue, or it is a fourth order or fifth order system. We can have multiple repeated eigenvalues. So how many, it doesn't matter how many repeated eigenvalues we have. For each repeated eigenvalue, we will get a separate Jordan block. Means if we have minus 1, if it is a fourth order system, assuming that minus 3 and minus 3 is again repeated eigenvalue, so it means that let's look at this simple means. If these lambda 1 is minus 1, lambda 2 is minus 1, lambda 3 is minus 3, and lambda 4 is minus 4. So the A matrix, the system matrix, will be, these eigenvalues obviously will be in this diagonal form. So the rest of the values will be, this will be a one Jordan block, 0 0 0 0 0, and this will be another Jordan block. So in this system we have these two Jordan blocks for each repeated eigenvalues. Okay, so I hope you have understood this canonical forms. So we have seen the four canonical forms: controllable canonical form, observable canonical form, diagonal canonical form, and the Jordan canonical form. But still, if you have any questions in this topic, please feel free to ask in the comment section. Stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuhu.